two instructions. One register, both want it. The first one currently works on it, but the second one needs the answer right now. This is the bug at the heart of every modern CPU. It's called a data hazard, but to understand data hazards, we first need to understand pipelining. The CPU cycle is always the same. Fetch the instruction, decode it, execute it. But what if while one instruction is being decoded, the next is being fetched? While the first instruction completes, a third fetch phase starts and a second decode phase. 3 instructions moving through the chip at the same time. The CPU just became 3 times faster. That's pipelining. Look at this. The execute stage is running an instruction, load R1. It grabs a value from memory and puts it into R1. Right behind it, the next execute instruction is already lined up. Add R1 and R2 together, write the result into R3. That instruction needs the value from R1, the one load is bringing in. But here's the problem. Loading from memory takes longer than the time it takes for the next instruction to show up at execute. So add arrives ready to run, but R1 isn't ready yet. Load is still waiting on memory. By the time the load instruction is finished, the pipeline could have processed 100 other instructions. This is called a data hazard. There are 3 ways to fix it. The simplest is to wait. When the pipeline detects that instruction 2 is about to read a value that isn't ready yet, it pauses and waits for instruction 1 to finish. Instruction 1 finishes its execute stage, writes the new value into R1. Now R1 is fresh. Now instruction 2 can move on. This works. It always works. But it costs you cycles. Every stall is a cycle the pipeline didn't produce anything. And the bubble travels down the line, every stage behind has to wait too. The clever fix. Think about a normal ALU instruction first. Instruction 1, add R1 and R2, put the result into R3. Instruction 2, right behind, subtract R4 minus R3, put the result into R5. It needs the value from R3. Same kind of hazard, but here the value comes out of the ALU, not memory. It's ready almost immediately. Now here's something to clear up first. We've been simplifying the pipeline as 3 steps: fetch, decode, execute to make it easy to follow. But in modern CPU architectures, that's not really what's happening. Each of those 3 steps is actually broken down further into smaller substeps. A real pipeline isn't 3 stages, it's 14 to 20. That means at any moment, there are 14 to 20 instructions side by side inside the chip, each one in a different substep. Why does that matter here? Because before we simplified the concept like this, 3 instructions moving side by side. But now we know they're actually split up into substeps. It's still basically the same. At the end, only 1 instruction finishes per cycle. But it matters. Say execute step 5 is where add R1 and R2 computes the result. Execute step 6 is where that result gets written into R3. But by then, subtract R3 minus R4 is already in the same cycle. It needs R3 right now, and R3 isn't there yet. That's why there's a clever trick. When the ALU finishes computing the result, the value doesn't get written into R3. The ALU uses a shortcut to write it instantly into the next instruction. Normally, the ALU's output would be to put the result into a register like R3, but because the next instruction needs it right now, there's an extra wire built into the chip for that purpose. That's a forwarding shortcut. For most data hazards, this completely solves the problem. The third fix doesn't even happen on the CPU, it happens way earlier when you compile your code. For context, the compiler is the thing that translates your code from programming languages into machine instructions, 1s and 0s. The compiler can already see the whole picture. It looks at the order of instructions and notices a problem. These two depend on each other. If they run back to back, the CPU is going to have to stall or forward. So the compiler shuffles things around. Same instructions, same final result. But now there's a gap. By the time add asks for R1, load has had plenty of time to fetch the value from memory. R1 is ready. No forwarding needed. The compiler didn't change what the program does. It just slid unrelated work into the gap so the CPU doesn't trip over itself. So 3 different ways to dodge a hazard: stall, forward, compiler reorder. Which one does the CPU actually use? All 3 actually. You're probably wondering, is the concept of pipelining even worth it? It looks like there are so many things that can go wrong. And yes, that's true. But let's look at the math in this case. Without pipelining, every instruction takes 3 cycles, 1 for fetch, 1 for decode, 1 for execute. No data hazards possible. If the CPU is running at 4 GHz, that's 4 billion cycles per second. So we divide 4 billion divided by 3. That's around 1.3 billion instructions per second. Solid, but slow by modern standards. Now with pipelining, the gaps get filled. In every cycle, 3 stages are active at the same time. That means 1 instruction completes per cycle. So at 4 gigahertz, 4 billion cycles per second, you can theoretically hit 4 billion finished instructions per second, 3 times the throughput of pure fetch, decode, execute. But is that real? It depends. The compiler doesn't cost cycles, it does its work before the program even runs. Forwarding doesn't cost cycles either, the value gets handed over through extra wires the moment it's produced. Stalls are the only thing that actually costs cycles, and when one hits, it doesn't just freeze one instruction. The whole pipeline behind it has to wait. On average, a single stall costs around 30 cycles of lost work. How often do stalls happen? Depends on the code. In well-optimized programs, where the compiler reordered everything it could, stalls are rare. Maybe 1 every 600 cycles, about 5% wasted. 5% off of 4 billion still leaves around 3.8 billion finished instructions per second. In code that hammers memory, lots of cache misses, lots of dependencies, stalls hit way more often. Maybe 1 every 30 cycles, 30 lost out of every 60. Half your throughput, gone. Half of 4 billion is 2 billion. So in the real world, you're getting somewhere between 2 and 3.8 billion finished instructions per second. Compare that to no pipelining, 1.3 billion. Worst case, pipelining still gives you 700 million more per second. Best case, nearly 2.5 billion more. The hazards are real, but pipelining still wins. Subscribe for more.